Okay, so today's webinar is based on modeling quench cracking. This really should have a little bit of side note here that says the quench cracking in steel alloys. While most metals that go through heat treatment do have like thermal strains and that can crack from those gradients there, steels add like an extra layer to that with the bulk density change of phase transformations. So when we talk about the modeling quench cracking today, we're talking a lot of phase transformations as well as the thermal strains. The agenda today is we're going to do a little bit of a background on DANTE. We'll do an introduction to the quench cracking. We're going to talk about factors that influence quench cracking. We're going to talk about modeling stress during quench cracking, the effect of phase transformation, and then we're going to use modeling to assess the cracking risk. We have a couple of case studies and examples here that include decarburization effect on quench cracking. We have two case studies that deal with induction hardening, one of a truck axle and one of a coupler. And then we have a last case study is on a 52100 bearing ring that was experiencing some cracks. So a little bit on the DANTE Solutions background. DANTE is an acronym for Distortion Analysis for Thermal Engineering. We were founded in '82 as Deformation Control Technology. So if you see some papers or publications based on DCT, that would be us. And basically focused on modeling thermal process of metals. DANTE Solutions has been focusing on heat treatment simulation software since the 1990s, when we were part of a large collaborative effort between industry, academia, and national labs to predict distortion in heat-treated steel alloys. And that ran from 92 to 2000. And that's really where the DANTE Solutions software came from. Since then, we have sole ownership of the software, and we've been developing it and changing and updating it ever since. The whole project started out of a need to control distortion and reduce scrap in the automotive and aerospace sectors. So definitely used, pinpointed for what we're doing now. Our main lines of business are the DANTE software licensing. We do a lot of heat treatment technology development, developing new processes using the software. And we also do a lot of consulting services for companies to develop the software. We're located in Cleveland, Ohio, right here on Lake Erie. Beautiful, sunny, snowy Cleveland, Ohio. And we've been doing pretty good in this business for quite a while. A little introduction here for the quench hardening. So during quench hardening, parts undergo extreme temperature change, leading to thermal stresses from temperature gradients. There's a volume change from phase transformations that occurs when you transform to austenite and then to martensite back and forth, or even to diffusive phases. The phase transformation from austenite to martensite, you can see down in the little figure at the bottom right here, causes high tensile stress to occur, which may result in quench cracking. And it's basically from the density change from the more dense austenite transforming to a less dense martensite that takes up larger volume. These high tensile stresses can cause premature part failure in service. And then the quenching crack leads to scrap parts, loss of revenue, and sunken time. So it's a big concern. So understanding the cause of quench cracking can help determine the ways to mitigate them. And then the major applications of DANTE over the years have been troubleshooting and identifying root causes and providing potential solutions to quench cracking issues. So the factors influencing quench cracking. So several factors that influence them are the quench selection. A more aggressive quenchant may increase the risk of cracking. But you also have to bear in mind to keep your mechanical properties if you go to a slower quenching. Material hardenability, like certain alloy grades, are more prone to quench cracking based on the chemical composition. Material defects can have a big effect on stress concentrations, including porosity in the material. When they go through heat treatment, those porosities can cause really high stress concentrations, causing cracks. Part geometry, like sharp geometric features, can cause stress concentrations from thermal strains. Process consistency, like part placement in the quench agitation, along with a combination above, may result in some cracks. And decarburization, like I said, we have an example on that later. But the lower surface carbon from decarburization results in a higher tensile stress state at the martensite phase at the surface. And this is usually a lot of cause of cracking. And all these factors can be modeled with DANTE. So how do we model the stress during quench hardening? So with DANTE, we use transient finite element models capable of predicting the nonlinear thermomechanical and phase transformation behavior in the steel alloys. You can see a lot of these yellow or orange arrows here all go into the computer model here. We use thermal boundary conditions, basically in the form of heat transfer coefficients, that we apply to surfaces to represent the heat transfer interaction of the part with the surrounding environment, such as the furnace, the quench vessel, and so on. We have phase transformation kinetic models that predict the phase transformations and associated with transformation strains, and this is really kind of a big part with steels here, like we talked about earlier. And then our multi-phase plasticity model determines the yield criterion of the phases. The strain rate, the temperature, and carbon content all go into that multi-phase plasticity model to really get the mechanical properties down. And what we get out of it is microstructure. You can see on the contours here below. So you can see the different phases in the microstructure of the part. So different martensites or different phases of the material. We get dimensional changes, so we can predict the distortion that occurs. And then more importantly for quench hardening, quench cracking here is the residual stresses that occur during the process or even after the process. So the effect of phase transformation. So quenching causes thermal and transformation-induced stresses. Basically, at the basic level here, the temperature gradient between the surface and the subsurface region causes different phase transformation rates as well. So there's a temperature gradient that causes a phase transformation gradient. And up here, I have a little example of a one element deep finite element model here, where this would be the surface. You can see the blue color represents a cooler part, and then the red color represents the hotter core of the part. And in an uncarburized part, the martensite transformation from austenite occurs where the temperature is the lowest. So here it would occur first at the surface when it drops below martensite start temperature. The higher density austenite transforms to lower density martensite, and there's a volume expansion. So you can imagine this area would grow when that martensite is formed from austenite. Then, once the subsurface cools down to MS, this one begins to transform, and when that transforms, it grows as well. This pulls the surface that has already transformed into tension. If the surface stress is too high, a quench crack can occur due to the brittleness of as-quenched martensite. So over to the right here, we have a kind of little animation that's running here that basically shows the heat treatment process and the phases for the steel. Upon heating, it goes up to the austenite start temperature. It drops in density, drops in volume, increases in density, and then when it converts to austenite. And then as it's cooled, it converts to martensite, and you can see the volume expansion here on the dilatometry curve here. That large volume change here is what we were talking about with pulling the surface into tension here. So these stress reversals are nonlinear, and then plastic deformation alters the yield of the behavior of each of the individual phases here. So if there is some sort of plasticity involved, it can alter the yield behavior of the phase. There might be some work hardening or something that goes on during the process. Simulation can be used to better understand the effects of phase transformations, the process sensitivities, the part design, and then the material hardenability on the possibility of quench cracking. So using modeling to assess the quench cracking risks, so the predicted in-process stresses and microstructural phases from the model can help assess the risk of cracking. The risk of cracking increases with higher tensile stress, and especially when the microstructure is in the martensite phase. A lot of time when we talk about the cracks, they all happen usually in the martensite, as-quenched martensite phase. Austenite, tempered martensite, and other diffusive phases are more ductile compared to martensite, reducing the crack risk. If we look at the figure over here on the right, we can see what we mean by the brittle. When the stress is, or the strain is applied, it begins to stress, and when it gets to a certain level, it just breaks. And you can see the little tensile specimen here. It's just there's no ductility involved there. Whereas a more ductile phase here would do the same, come up, and it would start to yield at some point here, and you can see the necking and stuff on the sample here. This shows the difference in the elastic deformation here. Plastic, sorry. So computer modeling is an effective approach to investigate the cracking issues. A sensitivity analysis can show how the part responds to slight changes in the quenching speed, the direction, and temperature. And modeling should be used to aid the design of new processes to reduce the risks of failure before problems arise. So that's all into the background here. And now we're going to talk about a couple of case studies. One is the decarburization effect on quench cracking. So in general, decarburization occurs when an austenitized part is exposed to an atmosphere containing oxygen. And what happens is that oxygen helps pull the carbon out of the near surface, and results in a lower carbon value at the near surface of the part. And this reverses the carbon gradient from the case of the core, so the surface has less carbon. And then the shallow layer of residual stress tension may form, leading to the spalling failure that you see in this gear below. And the slight decarburization may cause the high tensile stresses during quenching, which can also crack, hardening to before tempering. This example, the spalling was occurring in a large gear, and DANTE was used to investigate and determine the cause. This gear was carburized and oil quenched, and so compressive residual stresses were expected from the carbon case here. Kind of talk a little bit about that here is without decarburization, DANTE can predict the compressive residual stresses in the gear surface after quenching. So you can see with the minimum and maximum principal stress here, you can see the compression here along the tooth surface. And that's because the transformation to martensite from austenite happens at the case core interface first and then works its way to the surface. It kind of goes from the inside out almost. And what happens is that those volumes expansions keep kind of adding up until you get to the surface, and it pulls the surface into compression from the last transformation there. So in the ideal condition, compressive stresses should prevent the observed spalling. After discussing with the customer, the process includes a long air transfer time. So when they take the part out of the austenitizing furnace and bring it over to the oil quench, it has a long duration there. And during that time, we believe the decarburization happens. And so this would need to be included in the air transfer step. So with a model that includes the decarburization here, it's kind of hard to see on this little contour here, but at this exploded view, you can see that the level of carbon here is lower than it is on the subsurface. And the plot kind of illustrates that a little better here. It goes down to about 0.4 carbon at the surface before returning to the 0.8 that was expected, and then it travels down, diffuses through the parts after that. So the air transfer was only about a minute, and the simulated decarb layer is only about 1 millimeter deep. In DANTE, the decarburization, the way we simulate that is using a diffusion model where the carbon potential is set to a value lower than the surface carbon, and so it kind of lets the surface kind of gas out the carbon there. And this captures the effect of oxygen removing the carbon from the part surface. And the big thing here is the lower carbon equals a higher MS. So martensite start temperature. So when the part is actually quenched, the outside transforms first, and then the subsurface transforms. And that's the problems that we talked about earlier, where that when that inside transforms, it pulls that surface into tension. And since it's as-quenched martensite, it can crack easily under high tension. So when we run the stress model here, the maximum principal stress distribution with the decarbonization model, the predicted stress magnitude is very high. You can see the peak is at 1200 MPa, but the depth is very shallow. It's only about 0.3 millimeters. And this depth is greatly affected by the depth of decarburization. So, obviously longer decarb would give you less carbon near the surface, and so it can give you higher tensile stresses. This tensile stress is enough to cause the spalling effect that we see in the actual gears. The carbon effect on the martensite transformation, I kind of talked about that again, but I'll kind of reinforce that a little bit, how the surface transforms first here, given the higher MS, the lower carbon at the surface. And then once this region transforms, it pulls that into tension. So given the model here, we were able to see the issue, and the recommendations were made to modify the heat treatment process to reduce the spalling. So next case study we have is induction hardening truck's axle shaft. This axle shaft was experiencing high potential residual stress in the core, and there was some subsurface cracking and fractures that were happening during service. And it's really difficult to measure and quantify those without modeling because the inspection methods on the surface can't really capture it. You have to use something to see inside. So the axial dimension of the shaft was also a concern. It was increasing inconsistently after hardening, and that was causing some assembly issues. So DANTE model was used to investigate the root cause of the tensile residual stress and the axial dimension change. You can see the axial change here. And so we used a Joule heating method to mimic the induction heating, kind of mapping the temperature profile from the modeling. Since we don't really model the electromagnetics, the Joule heating works really well for this process. On the outside, there was a spray quenching boundary condition, and that is applied to the scanning speed of the inductor. And then the gap between the inductor and the spray line was used to model this. The shaft is kind of long, it's over a meter long, and it's about 35 millimeters in diameter. So when we set up the heat treatment model, we set up what the material we have is 1541. Again, meter long, and then there's a flange on one end here, and you can see that flange a little bit on the previous slide here. This is a cut open view, so we can see the inside. And then, so when we model it, they give us the process description. This is a two-turn inductor coil with quenching nozzles, as shown at the bottom here. You can see these hopefully on your screen. They're very tiny, but basically the inductor goes through, and then the spray trails it to quench the martensite afterwards. The process here includes a dwell at the beginning, and then a quick kind of jump in speed, and then an averaging of the speed and spray throughout the process. The spray quench is about an inch below the inductor, and then the quenching is a 6% polymer solution that was used. So for the heat treatment model, we modeled one sector of the shaft, basically one of the splines, and cut it down the entire length using symmetry on the axle. We could also use symmetry in two ways here is because of that, the axle is spinning, and so there's really no circumferential difference in heating around the part. So we were able to basically use this model here to accurately represent the induction heating. We packed about 60,000 elements into this model, with more elements here during the case region to capture the really high gradients and the stress concentrations in the part. And then we used power distribution profiles that were mapped using that joule heating that we were talking about from Fluxtrol. Did some great work here about the EM modeling, and they gave us the temperature history that we can use for the flux. Excuse me. And here we have a model of the contours, left to right. We have the temperature, and we can see where the inductor is with the red spot, where it's heating that temperature to above 1,000 degrees. And then about an inch afterwards, it's being quenched. And you can see that with the blue here. You can see the austenite phase being developed as it gets heated up properly. And then the martensite phase trails behind it, and you can see that's left over as it scans up the process. You can also notice there is some compression on the surface, and then there is some tension here leading and then trailing the inductor. And there is the axial displacement is shown at the end here as well. The big thing is really these stresses, the compression on the surface, and then the subsequent tension in the core otherwise here. So, the results of that showed us, you can see the middle section here that was done with the 12,000 watts per meter. Let's see, boundary condition, quenching boundary condition here, where it shows pretty significant tensile stresses along the core of the shaft, with more near the flange end, and it shows a good compression at the surface of about 750 MPa. The reason we see kind of like the difference here in stress, and there's a big peak stress, is with induction hardening, the near surface is the region that's transformed, and compared to like a furnace heating process or something like that where the whole body is heated, there needs to be a stress balance. And induction hardening, if you only transform that smaller surface, you have to have a stress balance from that compression only in that near surface. So we usually see a very high tension underneath the induction process because of the stress balance there. We did a pretty exhaustive case study on this project here. So we looked at 3 different quench rates, first of all, since that was one of the levers that they could pull. So we had a reduced quench rate to about 5,000 watts per meter, and then 25,000 watts per meter here. So basically a higher and a lower quench rate based on that baseline model. And the findings or the results for that was the core tensile stress increases with quenching rate. So the higher the quenching rate, the higher the level of core tensile stresses that we saw. And then the axial distortion also increases with the quench rate. You can see that with the contour here on the right. With the higher quench rate here, the 25,000, we ended up with an axial displacement of over 2 millimeters, 2.3 millimeters, where we had about 2 millimeters for the baseline model, and then the slower quenching rate gave us a result here of about 0.5 millimeter or so in length change. The slower quenching rate also gave us lower compression of the surface, and then obviously a lower tension to balance it out inside the part. So as long as we reach the mechanical properties here, that one will work pretty well. The circumferential stresses are shown here as well. They mimic the axial stresses for the most part. There is a higher magnitude of stresses, compressive and tensile, in the higher quench rate model. Other important processes that can be investigated that we didn't do for this study was the scanning speed of the inductor and the inductor width. So effective deheating time, so the larger heating region or the speed at which the inductor moves. The power and frequency, so that the temperature can get up to, and then the depth of the inductor. We can adjust that as well and see the results of material response. The dwell time could have a good effect before the spray quench. And then all these parameters are expected to affect the case depth, residual stress, and distortion of this part. So what's nice about modeling is we can do a deep dive into the part response. So basically, we don't just see the black box. You put the part in, you get the part out, and what you get. So we're able to step through and see critical regions. One of them that we noticed was at 16.5 seconds. The inductor is moving up at its constant rate of 8 millimeters per second, and the lower area is actually being spray quenched. So these are just kind of results in that 16.5 second time during quenching. And left to right here, we show the temperature. You can see the region that's being heated by the inductor, and you can see that it's being cooled underneath already by the spray quench. We can see the austenite phase being formed from the temperature reaching AC1 here. And you can see that it's not completely uniform down here because some martensite has already begun to form at this time. It is about 94%. It is almost nearly complete right at the surface here. There's still a little bit more to go as it goes up and cools. But right now we do see in the S33, the hoop stress region here, we do see a line of tensile stresses being formed under the case here. And again, just to kind of drive it home, the stress balance here is really the most important thing. Only this region is being transformed into austenite, and then this region is being transformed into martensite. So it really only has this region to have the stress balance. And so it has this compression here. It needs to have some sort of tension in order to balance it out, and has this volume to do so. And that kind of drives home and shows the phenomenon of the volume expansion from the martensite there and its effect on the underlying element or underlying material. We also plot the radial displacement here, and this bulge here is shown basically from the heating, the thermal expansion here. It kind of expands the shaft as it pulls out. And then the U22 shows the length change, overall axial displacement in the shaft. Continuing with the deep dive is we can see the part response during the induction hardening here. So 4 points were modeled on the shaft, or 4 points were selected on the model to show the depth. We have one on the surface. We have one at about 4 millimeters down, one at about 8 millimeters down, and then one representing the core. And these 4 plots here show the effect of the material as the inductor passes over and is spray quenched. We starting left to right here, we have the temperature, and so we can see that the surface reaches a little over 1,000 degrees C, and the 4 millimeter point here goes up to almost 900, and both of these kind of transform to austenite here. These 2 points below don't transform; they only get up to about 700 degrees here. And so the depth of transformation here is really within the case here. We have the fraction of phases as well, so we can see that the austenite is formed here really quickly between A and B, and then the surface transforms, and then the core, or the 4 millimeter point, transforms slightly after it. So we can see the fraction of phases that are occurring. And then this kind of all leads to some important stuff, the stress reversals in the part. So we can see the axial stress here. And we can see, we're starting with the blue, which is the surface measurement. You can see that it goes quickly to compression here from the heating, and then it works its way up. And then once it starts to transform to martensite, it has another drop down to compression. And then through this phase transformations, it finally ends up at a higher compression here. So it kind of shows the stress reversal from compression to tension to compression that happens during the during heat treatment. during the phase transformations. The next one is the green one here. You can see it does kind of the same thing, only a little bit more muted from the phase transformations below it. And it goes again from tension to compression and then back down into compression here. The part in the core, just for contrast here, goes quickly to tension and then back down to compression as the martensite transformation happens, and then it goes back to tension in the core. And you can see these are pretty high values for the tension here. And lastly, we have the axial displacement. We can see, the part length change here in that section. We can see, basically heating up through thermal expansion here, and then cooling back down the radial dimension here. And then we can see the same thing at the radial displacement, the bulge that we saw in the contour earlier, quickly spikes up here to about 0.2 millimeters and then comes back down. Has a little bit of a jump here from the martensite transformation, and then back down to regular levels here. So a lot of this really helps us see what's going on in the part as it's being heat treated, and it's really effective to be able to step through and see these issues happen as they occur in the part. So lastly, the last thing we did was they suggested that we try three different materials, or two different materials. We had the baseline 1541. We also looked at 4140 and 1040. All of these are 0.4 carbon here, or just about. And you can see the table down below. They all have kind of similar martensite start temperatures. They do have very different DIs as far as like hardenability. And so the results of them show they are all kind of in the same range as far as the residual stresses afterwards. There isn't very much change between the three different types of models, but we do expect with a higher carbon, like say 0.6 or even lower carbon 0.2, we may see some very different results here in the residual stresses. But since they all are about the same carbon, they all behave relatively similarly. 1040 does have the lowest hardenability. You can see here the DI is only about 30 millimeters. And we do see some bainite phase during quenching or after quenching in the core. And whereas the 1541 and the 4140 transform to martensite only in the case. And this is really kind of useful in part design and material selection. So if you wanted to test different materials, you can look at it and see what kind of response would happen with the same heat treatment schedule that you would use. Our second example case study here is induction hardened steel coupler. We're transmitting torque through shafts here. And this one, again, uses a induction hardening process, a scanning induction hardening process. You can see the part here and then the model quadrant. Here, thing kind of to note here is it's kind of like a rectangle hole inside of a circle. So there is some section thickness, and I'll talk about that a little bit more here, difference. DANTE was used to investigate the induction hardening process to identify the reasons for the cracking that they see in the corners here, and then to give a process modification to eliminate the cracking problem. Three processes were evaluated per the customer recommendation. They wanted us to modify or model the original process or the baseline process, a process which produces a reduced case depth, and then a process that includes a preheat. So building the model again, this one was made of 4340 steel. It has a case depth of about 4 millimeters, and the width of the inductor is about 100 millimeters. You can see the inductor here at the bottom right. The inductor travel speed is about 3 millimeters per second up the shaft, as you see it on the part here. And then the dwell time between the inductor and the spray start is about 10 seconds. So it heats up for about 10 seconds before it starts to spray. Power distributions and functions of time and geometry are estimated to mimic the induction heating. Again, we use the joule heating modeling here based on the frequency and the power of the inductor, and basically targeting the case depth that they requested here. So we used a core model, again, using symmetry as best we can. We used finite elements on the inner diameter of the surface. We used much finer to capture the gradients of temperature, phase transformation, and then any internal stresses that are formed from the induction hardening process. The moving spray quench was modeled using DANTE immersion quench feature. It's kind of a nice subroutine used for quenching these. So the original process, or the baseline process. So the figures on the right show the maximum principal stress and the martensite phase. The maximum principal represents the hoop direction that we're really showing the experiencing the quenching here, the cracking that they experience. It kind of dominates the quenching. Um, so for the selected residual, sorry, the selected critical point here, actually you can see it in the figure in the bottom right. We show the temperature history here, where it starts off at room temperature, and then it spikes up to about 900 degrees on the surface and the corner here, and then it drops down and quenches to martensite, and then there's an eventual air cooling afterwards to get to room temperature. And so again, we just like we saw with the induction staff, we have a compression here due to heating, and then as it's kind of balancing out here, it goes back up to tension here. You can see that the residual stress is actually on the secondary on the side here, and it gets to about like 650 MPa and then transforms to martensite, and you can see the compression that's formed from that transformation. And then when it's cooled and quenched completely, we see it goes back up to tension. It gets up to almost 800 or so MPa here, and we believe that's when the quench cracking actually occurs in the part due to the martensite phase. So that high tensile stress based on the kind of the temperature balance or rebalancing in the part, and then the as-quenched martensite tends to crack under tensile process stresses. You'll be hearing that a lot today. Okay, so the next model we did was the one with the reduced K-step, and the idea here was the customer believed that less transformation here would cause less tensile stresses and probably reduce the cracking. They never ran one like this, so they wanted to see a model first to see if it could kind of help solve the problem. The model results show that the simulated stress is approximately the same between the baseline model and this reduced K-step. And this is a pretty significant finding for them that saved them a lot of time and money by eliminating an actual physical test. You can see the time temperature results here, and you can see the hoop stresses here. It still has a pretty high magnitude. This section here that's very hard to see is actually exploded down to here. And again, it shows the same story that we saw with the baseline model. We start off really neutral, and then it goes into compression. And then once the martensite transformation, we go back to compression here, and then it ends up a little lower magnitude, but still problematic as far as the quench, the cracking that's observed. So the last model they requested was the process with a preheat. This part was preheated before induction hardening, and it was modeled to be done by the furnace heating, so taking it out of the furnace and then induction hardening afterwards. This also can be done with the low frequency induction heating. The induction preheating has some advantages over the furnace preheating, and all of these can be modeled here with DANTE, mainly kind of just speed that they can do, hit it with a low power, low frequency, and then do the actual hardening process afterwards. The uniform preheating temperature of 260 degrees was used, and this is just kind of assumed. We can also look at different temperatures, and optimize them, but for this one we used the 260 degrees. So due to the higher initial temperature, the power used for the inductor was reduced by about 70%, or to about 70%, to produce the similar K-step. And this keeps all other process parameters like the quench and scanning speed and everything the same. After quenching, the corner fillet reached a peak stress of probably of about 550 MPa, as shown in the figures here. You can see the hoop stress again is on the secondary, and the cracking possibility is greatly reduced by this magnitude being much lower. We can see, let's start here with the temperature. It's about 260 degrees to start, and then we see we heat up to about the 800 degrees or so in the corner there, and drop it down to room temperature with the quench. And you can see the same kind of stress reversals here. We go into compression here from the heating. We go into a little bit of tension here from the continuing the heating and the balancing there, and the material around it forming. And then we have the transformation of martensite, which brings it back into compression. And then it does go back into a little bit of tension, like I said, about the 550 MPa, before actually cooling down completely and going back into compression overall. The reason this one goes down into compression here is because the whole part was preheated, and then so the whole thing has to shrink down thermally, and when it does so, it increases the compression, and it turns this part back into compression for that. That compressive residual stress is really good. It benefits surface fatigue, and you know, it really helps with wear and stuff on the coupler itself. So you really kind of want that before the process, we believe. And that's, again, caused by the thermal shrinkage after transformation. All right, our last case study here has to do with the 52100 bearing ring. This ring is hardened by a press-quench process, and a high percentage of, about 60% of them are cracking. There's the ring geometry, and it's about a 4-inch ring here. And the outer surface has this little concave shape, as you see here for the bearings to ride on. The material again is 52100, and the DANTE heat treatment modeling is used to find the root causes of cracking and solutions. We used a 2D axisymmetric model for this, so we basically took this whole section, took the cross section, and was able to model that in a 2D way with the contact from pads on the top and the bottom, and then the expander in the inside. Here's an image of the quench crack. I hope you can see that on your end. It shows the cracking along the outside edge of the race here. So with process modeling, we have the maximum principal stress here, shown in the contour here. We have the temperature of the part. You can see it being quenched right now. And then we have the martensite transformation happening right there, the volume fraction. And the important and critical part of this is right about here. When the martensite transformation is pretty much complete on the outside, the core begins to transform. You can see the more of a green color here, whereas the outside is all as-quenched martensite. And then when this begins to transform, it's being held in by the pads on the inside, the top, and the bottom. And really the only way for it to go is out this way with the volume expansion. And you can see that results in a very high peak stress around that region where they're showing the cracks. So there's a little more exploded view in the timestamp step here. So that, again, we have the crack, and we see the high tensile stresses. You can in the core here, you can see it is kind of a little bit in compression. That's because the martensite is transforming here, and it's basically pushing out. You can imagine arrows pointing out in all directions here, and it pushing out like that. The only way it can go is out this way, and it opens up the bearing race. It causes high tension in the martensite phase. So 52100 has a really high hardenability, and the austenite transforms basically to martensite during the quenching process, or only to martensite during the quenching process. That austenite to martensite transformation, the core is delayed compared to the net at the surface, and this delayed martensite transformation and the volume expansion associated with it causes surface tension and stress in the outer layer, we were just talking about. For this model, we also used the ring surface on the top and the bottom here. They kind of stick to the press-quench dies. And this, we found that the pulsing load is not applied during the press-quench, even though it does have the pulsing feature. And a lot of things can cause it to kind of stick here. Some of them were like the tooling wear of the actual press, from continual use. It could cause it to have uneven or uneven load or friction on the part while it's being processed. They could also have like machining tolerance for the ring itself. Could be a little off, and then they would have higher and lower load regions, causing more friction in tooling as well. So solutions. So we have several models that we worked with here. We had some sticking model here with the normal quenching rate. We also had an adjusted quench rate because the customer said that they can do a lower quenching rate by reducing the oil pump power. And we have to make sure that the quenching rate is fast enough for the hardness and mechanical properties that they need to for the bearing ring. So we wanted to run the model to see those as well. And the idea here was to reduce the gradient, the temperature gradient, which reduces the transformation gradient between the core and the surface here. So we have the 4 models here, and you can see that it's about 860 MPa in the sticking model here. When the part was more free to move with the pulsing load, we reduced the tension that was being seen during the process here. This one was with a higher quenching rate, and so it actually increases it compared to the pulsing load. And then the last model we did was a lower quenching rate, what we talked about, and it reduced significantly the tension that was shown on the outside edge. So the 4 batches that they ran some experiments here. The first one was the kind of baseline that they had before, and they ran it with the no pulse, and you can see a lot of them were cracking about 60% or so. They ended up running a batch with pulse, and only 4 of them cracked during tempering, and none of them after quenching. They redid the first test here, and it had similar results to the number 1 test. And then the pulse load with the reduced quench rate resulted in no cracks whatsoever through the entire batch. So I'd say that's a huge success. And then so kind of shows, again, we can do the deep dive here with the stresses here in the process. The red arrow shows the difference between the maximum in-process stresses between the reduced quench in blue and the press-quench in purple. The press-quenching rate is a lot faster than the reduced quenching rate, obviously, since it's reduced. And we can see that the martensite transforms really quickly through the process here. Whereas when the martensite is transformed with the reduced quench, it's a little more gradual. You can see the slope is a little more gradual when it's being transformed here. And this results in the quench rate and the increased friction results in the high tensile stress in the press-quench condition. All right, so summary. The strain and material The strain and material volume change caused by phase transformations during quench hardening plays a significant role in the internal stresses and cracking possibility. Highest tensile stresses in as-quenched martensite determines the cracking possibility. It's really kind of the big takeaway of today here. Stress concentrations caused by part geometric features should be considered. So when you have the strains in the part, basically thin, thick sections, you will have a lot of stress concentrators in sharp geometric features. Material cleanliness should be considered, or surface condition effects on the cracking possibility. So if you have inclusions or porosity in any way, that those can affect cracking because they're good stress risers. Surface decarbonization was shown to have a big effect on the phase transformation gradient. The temperature gradient or phase transformation gradient in the part during quenching has a significant effect on the magnitude of those internal stresses. Quench cracking risk can be reduced by lowering the peak stresses during quench hardening. Process changes like using a protective atmosphere, proper quench and agitation, and material and part design changes can be considered to help lower the quench stresses. And then DANTE heat treatment modeling can be used to troubleshoot and evaluate potential solutions to quench cracking or to evaluate new processes to assess the risk of quench cracking. And that is the end of my talk. I hope you guys found it very informative. We can move to the Q&A section. We'll try to answer any questions that you may have. Looks like I got one. It says, will this presentation be shared with the audience following the webinar? And I said, yes, I can send it out, no problem. Making a note to share that. Is there any other questions? We can let them come in. And if you do have any other questions that you don't want to put in the Q&A, we can you can always email us at support@DANTE or visit our website. There are a lot of information there. It's on our publications and our case studies. A lot of these case studies are actually on the site there, so if you wanted to take a look at those. Great. I'll give a few more minutes just for questions. Okay, I think we can end there. Again, if you have any other questions, give us a call or give us an email at support. And we thank you for your time. I hope you found it informative. Thank you.